Hello, today we're going to talk about properties of the equilibrium constant. Okay, so you have to be able to manipulate K. So let's look at if this is our original reaction, and this is our original expression. C is on the top because it's a product, and A is on the bottom, it's a reactant. B squared is on the bottom because it is a reactant and the coefficient becomes an exponent. Okay, and then the K value for this one is 100 for this imaginary reaction. If you were to flip a reaction around, so products become reactants, reactants can become products, your expression flips top to bottom because the A and the 2B are now your products and the C becomes your reactant. So because the reaction's flipping, the K also flips, but it flips top to bottom. And because of that, since you're inverting the fraction, you're going to take the inverse of K. So if you take 100 to the negative first power, you get 0.01. And you want to do that no matter what the value of K is. Anytime you flip the reaction, you take the inverse of the K to find the new value of K for the new reaction. Now, if you have that same original reaction, but let's say you want to multiply the reaction by a factor. Now this one is multiplied by 2. So we have twice as many A's, twice as many B's, twice as many C's. Well, the coefficients are changing. So in this case, we have 2 C's now, so C is squared. A is also squared, and now B is to the 4th power because I have a coefficient of 4. And we can simplify that by saying that the whole expression is now squared because everything is multiplied by a factor of 2. And because the whole expression is squared, we also need to square our value of K. Now, any factor that you happen to multiply the reaction by, you're going to raise K to that power. So in this case, our 100 is going to be squared, which will give us the 10,000. But if you multiply the reaction by 3, then you would take K to the 3rd power. And that would be your value for K. Now, the third thing here is that if you're adding reactions together, so just like we're doing with like kinetics when you have multiple step reactions, if I were to add these two reactions together, the C's cancel, it's an intermediate, but we wind up with A, 2B, and D as reactants, and then 2E as our only product. So our new equilibrium expression is here. Essentially, if we were to put these two together, so let's see, we have C over A and B squared, and then we have E squared C and D. Okay, so basically I just combined the numerators and then combined the denominators like I was multiplying the two fractions, but you'd notice that the C's would cancel out, and that would give you your overall reaction. So because multiplying the expressions gives us the new overall expression, we need to multiply the values of K to give us the new value of K when you're adding them together. Okay, so for this example, we need to use the first two reactions here to add up to the third reaction. Now this one's a lot like Hess's law, or really all of these problems are a lot like Hess's law, but you're going to perform different operations to K than you would for heat. But you still want those two reactions to add up to the final overall. So you'll notice like we have the same number of A and the same number of C, but for E here, we've got just one E when we need 2 E's. I want to go ahead and multiply that whole reaction by 2. So I have 2D plus 2B yields 2E. And then when I multiply that whole reaction by 2, I'm going to raise K to the 2nd power. So that will be 15 squared, or 225. And I like to cross out reactions once I've used them so I don't confuse it later on. That way, now that I have these two reactions, A stays the same. We have a total of 3B. Our 2D cancels out, and we have 1C and 2E. So that adds up perfectly. So because the reactions add up, you want to multiply the two values of K. So you'll do 225 times 5, and you'll get that the overall value is 1125. Very large value of K, definitely going to favor the products. Okay, for our last example, we have 3 reactions and their values for K, and we want to find the K for this final overall reaction. So it looks like, HXCl, it's on the correct side, correct number, so that value of K is good. OH negative, it's on the wrong side of the equation, so I want to flip that reaction around. We'll do H plus OH negative yields H2O. So when we flip the reaction, we want to take the inverse of K because we're flipping top to bottom reactants products. So the inverse of 1 times 10 to the negative 14 is 1 times 10 to the 14th. So positive 14 now. So there's that. And then the X negative 2 is also on the wrong side of the equation. So I want to flip that one as well. HX negative, X2 negative, and H plus. Let me go ahead and cross that one out and that one because we've changed them. And since I flipped the reaction, I want to take the inverse for K. And when you do that, you get 1724. And then finally, you're going to add up all 3 reactions. Let's make sure everything that cancels out does cancel out. So the H plus is on the product side and the reactant side. And the HX negative is on the reactants and then the product side. It looks like everything else is good. So that's great. We're going to, since all 3 of those reactions add up properly, we're going to multiply all 3 values of K to get the K for the overall as, looks like we're using 2 sig figs, so 1.1 times 10 to the 27th, a huge value for K, so it essentially goes to completion.